this is the LSC accelerator, and here we are in Atlas, and CMS is over there. They are all 100 meters or around 100 meters down, the detectors. And the protons are colliding in the middle of the detectors because new particles should be detected inside the detector. I mean, they should not be escaping from some holes and so on. It should be hermetic, the detectors. And so each bunch of protons, there's 750 meters, which means 25 nanoseconds apart from. I mean, every 25 nanoseconds we collide two bunch of protons. What I mean bunch is 10 to the 12 protons coming from one side, 10 to the 12 protons coming to the other side. And few of them are colliding. And we are selecting only one of the collision. And even so, it makes around 1 billion collisions per second. And it is impossible to store all this data. We are using different filtering methods, and at the end we select only 100 events per second. And this is also a huge amount of data. You cannot store anywhere. They are distributed all over the world, and there is a internet system called GRID. We are analyzing the data through GRID system. And you can see different sub-detectors here. If I stop this one, for example, inner detector, there you can see different types of detector. For example, these are the silicon sensors, which is in the middle of the atlas, to trace back the particles, where do they originate, because at the same time there are cosmic rays coming all over the space, and they are hitting the detector. They create some trace in the detector, so one has to eliminate this background. So therefore the inner detector is very important. And how will we go forward? It starts from the beginning. After that, there is calorimeters, for example, around the trackers. Calorimeters measure the energy. For example, here you see one calorimeter down. How you can detect the energy of a particle, very small particle. When the high energetic particle passes through the absorber of the calorimeters, they create secondary particles. They release their energy, and the secondary particles, when they pass from scintillators, their scintillators are simple plastics, for example. They increase the atomic level of the scintillator. And when the atomic level goes back, which is very fast, of course, a photon is released. Photon is simple light. And these photons are collected with fibers, and they go to photomultiplier, where in photomultiplier, when the photons hit the cathode, they create electrons, and at the end you get an electronic signal. It is the same principle that your camera works, for example. Also, it is called photoelectric effect. It's a very well-known physical phenomena that Einstein finally explained and got the Nobel Prize. When the photon hits the photocathode, it creates an electron. And it is the same system in solar panel, for example. In solar energy works like that. When the sunlight, light from sun, which are photons, hits the material, they create electrons. And these electrons, at the end, it gives you an electric signal. In the detector, always we get some electric signal, and then afterwards, analyzing these signals, we can identify particles and so on. There are more videos here, but there is one upstairs, which is better. Here you can see different muon spectrometer, for example. Maybe you can see here better. This is a model of Atlas detector made by Lego. the protons are collided in the middle of around the collision point. There's tracking detectors which trace the which shows the path of the particles, and then calorimeters which measures the energy, and finally at the end you have muon system, because only muons can pass without interaction huge layer of material. Other particles, they release their energy before reaching to muon chambers. Here you see one of the muon drip tubes. When the muon pass through the tubes, it doesn't release all energy, but it leaves a trace, ionize the gas, so that you get again the signal. Only muons can reach up to that point. Sure.
So is that the reason that this is so big?
The reason that it's so big, it's the biggest detector, is 45 meters long in the world. The reason is that they chose a different type of design, which is small, relatively small magnetic field. For example, in CMS, we are using a 4 Tesla field, which is much big, more than the Atlas. Atlas has only 1 Tesla. The magnetic field is to bend the particles and to measure the momentum. So Atlas' choice was to use a small magnetic field, and therefore they have to be big to get this curvature. But in CMS, it is all compact. CMS is half size of Atlas, but it is much more heavier than CMS is the most heaviest detector in the world. Atlas is the biggest because it is a matter of design. So they are designed to cross-check each other. So they because only one detector claiming that they found Higgs is not enough to prove that it is Higgs. So both detectors should be inconsistent and so on, but they have different design. But in principle, all the modern detectors are always almost the same concept. I mean, like onion shells. In the middle, there is collision point, and then trackers, then calorimeters, then muon systems. You can see the control room here. People are working all the time, 7 days per week in 24 hours. Even there is no,
Interesting.
there is no collision. There are
Interesting.
here. Of course, we are close to the Christmas holiday. There's not much people left, but 1 or 2 people are checking the detector systems. There are many gas system, water system, electric system, so they should be maintained all the time. For the moment, collisions are stopped. They will start again in April. But it is still a little bit radioactive downstairs, so visitors are not allowed for the moment, but probably in the new year you would be able to go down to see the detector while you're there. So there are 8 hours shift every day for different sub-detectors. Okay. Any question?
Yeah.
Sure.
Why are you still running collisions?
Why?
Like, is there anything new to observe?
Hi, sure. I mean, as it was mentioned in the video, there are many things we don't know about the universe. We know only like 4% of the mass. All the mass that we know, the stars and other stuff, is not enough to explain many things. For example, there's something called dark matter, which makes the galaxies turn faster than we explain. There must be some matter which makes turn. I mean, it's called matter because it is only gravitational force. It is not electromagnetic force. It is not weak force and so on. Maybe there are some small particles around galaxies
huge number of small particles, but they are heavier, for example, maybe 1,000 times more heavier than protons. Maybe these are the speculations for the moment because we don't know anything about it. And there is also dark energy that we have absolutely no clue because our universe is expanding, accelerating. I mean, maybe you have heard Hubble in 1930s. He observed that universe is expanding, and that's why it is a beginning. But this expansion is accelerating now. So something is accelerating our universe. It's like anti-gravity for it. So we don't know many things, and standard model also is not okay. We found Higgs, but it is not explained in the standard model that why Higgs has so much quantum correlations. We are using some fine tuning to adjust parameters. So there are many unknown things, and there are many theories beyond standard model, some speculations, and that's why we are looking for new particles. We are looking some signal beyond standard model. In the video, for example, Fabiola showed a spike. So this was a spike which represent a new particle, which was Higgs. Okay, we are looking for something like that, a new particle, to explain more about the universe.
And how does one experiment differ from another? Like, what do you do differently? Is it the same?
CMS and Atlas, they are very similar. They are looking to same things. There are some signal beyond standard model. And there's also Atlas and LSCB. I don't know if you have visited them. They are mainly concentrated on heavy ion collisions. They are looking to quark gluon plasma and a difference in asymmetry between matter and antimatter. For example, LSCB, they are mainly analyzing B quarks to see the difference between B and anti-B. Because in the beginning of the Big Bang, we believed that there was only radiation. And from radiation, you can get two particles, but particle and anti-particle, and in equal amount. And this is not enough, I mean, to create an atom. To create an atom, matter particle should be a little bit more than the anti. So in the standard model, it is explained a little bit, but it is not enough to explain all the mass in the universe. So there should be some new thing. So they are more concentrated on this other stuff, something like that. So there is another video upstairs in 3D. It is much nicer. Want to go up and then